Hello. In this video, we're going to take a look at the idea of type 2 improper integrals. So if you recall from the beginning of these videos, we readdressed the fundamental theorem of calculus, which is written up in the corner. It says if f is a real valued continuous function on AB and f is an antiderivative of little f in that interval, then the integral from a to b is the antiderivative at b minus the antiderivative at a. And he said that the type 1 and type 2 improper integrals address these certain pieces. Type 1 looked at the idea of what if I don't have a closed interval? What if my interval is infinite? And we had type 1 improper integrals where we would turn a bound of infinity into a limit. The second type of improper integral is what if the function isn't continuous? In particular, what if there's an asymptote at some value inside the interval? Can we still find the area under the curve? Can we still find the integral? And so that is type 2. So with type 2, suppose we have something that's continuous on most of the interval except for one of the endpoints. So endpoint, not continuous, endpoint, not continuous. And at that endpoint, the limit goes to plus or minus infinity, meaning there's an asymptote. Something doing asymptote behavior. Then we're going to turn that problem into a limit. So when our problem is with the lower bound, we're going to make it a limit approaching from the right-hand side. So because we're looking over some interval from A to B, and we're saying there is an asymptote at A somehow, we don't care about what's on the left-hand side of A. We only care about what happens on the right-hand side. So we only do the right-hand limit. So turn that problem bound into a limit, and then we can evaluate from T to B of that integral, just like we did in type 1. When our problem is on the right-hand side, and it's our upper bound that's a problem, we're going to turn that upper bound into a limit by looking at T going to the upper bound from the left-hand side. Once again, because we're looking at A to B, and our asymptote is as we approach B, we're only worried about the left-hand side of B. We don't care what's happening over on the right of B. So turn it into a limit, and then we have the integral from A to T, f of x dx. And then our last case is suppose it's continuous from A to B except for some random point P in the middle. So we have A to B working, and some point in the middle B, we have a problem of an asymptote. Well, then we're going to break it up into two intervals. We'll go from A to P and then P to B. So we'll have the integral from A to that interior point, f of x dx, plus pick up at the interior point to B, f of x dx. And now, using limits, we can see this is an upper bound, that's a problem. So we would turn that upper bound into a limit. So t goes to p from, it's the upper bound problem, so from the left of the integral from a to t, f of x dx. Plus, now in this second one, the lower bound is the problem. So we'll turn it into a limit with a different variable. Z goes to p from the right, integral from z to b f of x dx. And then we evaluate those limits and those integrals as we normally would. So there are our rules for improper integrals of type 2. Just like with improper integrals of type 1, the first thing is to find where the problems are and turn them into limits. Now we'll take a look at an example of this. First example is -3 to 3 integral of 1 over the square root of 3 minus x dx. I'm okay plugging almost any value in, except I cannot make that square root negative, which making the square root negative would mean I'm plugging in something larger than 3, right? 3 minus 4 is -1. I can't have a negative under a square root. And the bigger issue in this case is actually I also can't plug in 3. Because if I plug in 3, 3 minus 3 is 0. The square root of 0 is 0. I can't divide by 0. Can't be done. So the problem point is that upper bound of 3. Can't plug 3 in. So we need to turn it into a limit. Using the rules from above, when the upper bound is the problem, we're going to use a left-hand limit. So turn that 3 into a limit of t goes to 3 from the left of the integral -3 to t f of x dx. And f of x is our function 1 over the square root 3 minus x. A quick rewrite to help us evaluate this integral. The square root in the denominator is 3 minus x to the -1/2. We add 1 and then divide. So the antiderivative will be limit as t goes to 3 from the right of 2 square root 3 minus x, because we added 1 to the exponent and then divided by that. But then there is also a value in front of that x. And just like with chain rule, that's going to affect our antiderivative. And it's a u sub effect where we're just going to divide by a negative. And dividing by a negative is the same as multiplying by the negative. So our antiderivative is -2 square root 3 minus x, evaluated from -3 to t. Plugging in our bounds, we get the limit as t goes to 3 from the left. I somehow changed them to rights. Of -2 square root 3 minus t. This a -2 square root 3 minus -3. what 2 square root 3 minus t looks like, just in general. It's a square root function that has been flipped. And if we add on that other negative, we'd flip it over the other axis. But in general, we have this square root function where approaching in from the left-hand side, that's okay. And we end up coming to the point of 0. If I plug in 3, I can do that now. I can take the square root of 0. So taking the square root of 0 makes this limit -2 times 0 plus 2 times the square root of 6, which is also just 2 times the square root of 6. So this tells us this integral converges. The integral from -3 to 3 of 1 over the square root of 3 minus x dx is equal to 2 square root 6. Or, using our wording, converges to 2 square root 6. Examples in the next video.